Imagine a drone flying along when suddenly one of its four motors fails. In an instant, the aircraft loses the balancing torque that kept it steady. Without that opposing thrust, the quadcopter will begin to spin uncontrollably around its vertical axis. In practical terms, a quadrotor normally has 6 degrees of freedom: 3 translational, up down, forward back, left right, and 3 rotational, roll, pitch, yaw. But with only 4 motors, it's already an underactuated system. Losing one motor makes it even harder to control. When a rotor quits, the yaw torque from the remaining motors can't be countered. As one of the analysis points out, with 3 motor controlling 4 outputs, roll, pitch, yaw and thrust, you end up with a 4x3 control matrix that cannot be inverted. In other words, you simply cannot control all axes independently. The inevitable result is an unwanted spin. In this project, we tackle that problem head on by deciding to abandon yaw control and focus on what can be controlled. Our key insight is to let drone yaw freely instead of fighting the spin. Yaw, rotation around the vertical axis, becomes uncontrolled after a motor failure, but the drone can still use thrust and tilt to descend safely. In effect, we relax the yaw constraint. This is a known strategy. As one expert notes, if the goal is simply to stay in place while allowing the craft to pitch, roll or yaw freely, it can hover even with one motor. By giving up one on precise yaw control, the quadrotor still has 2 remaining control inputs, vertical thrust and one tilt angle, which are enough to guide it down gently. In practical terms, we control up thrust, that is vertical lift, and pitch, tilting the drone forward and backward, as the 2 active factors. We shut off the opposite motor. If one fails, its diagonal partner is turned off to simplify control, and focus on modulating the throttle and pitch angle to descend. This drop in control degrees of freedom is illustrated by saying the system goes from 3 translational plus 3 rotational control to effectively 1 translational to 1 control, thrust and 1 tilt after the failure. See how we model this situation. In our system model, we note that a failed rotor creates a net unbalanced moment around the z-axis, that is the yaw axis. In normal flight, 2 rotors spin clockwise, 2 counterclockwise, cancelling yaw torques. But if one motor quits, that symmetry is lost. The drone will start spinning unless something is done. Mathematically, one can show that with one motor off, the mapping from rotor speeds to torques becomes unsolvable for yaw, a 4x3 matrix. You can't invert it to get a unique solution for all axes. Our motivation is to simplify the control model by removing yaw from the loop. So, we model the damaged quadrotor as having only 2 effective control outputs: vertical thrust up and down and pitch control, forward backwards, tilt. With yaw ignored, the system can be stabilized using a reduced set of controls. As you can see, in a normal condition, the quadrotor has all 4 of its rotors working, but in our condition where one of the rotor fails, we switch off the opposite rotor and model it as a bicopter and try to control the throttle and the pitch for the drone. But first, how do we even know a motor has failed? Before any emergency control can kick in, the system must detect which motor has failed, and this should be quick. We implement a custom digital filter to do this. First, we take the current vehicle attitude and also the vehicle attitude set point and find the error. This error is passed through a bandpass filter, which filters out only these errors which fall in the 3 Hz to 9 Hz range. Anything below 3 Hz, we found out using empirical data that this was due to some low frequency drift, and anything above 9 Hz was due to some noise. This filtered attitude errors are then differentiated to find the rates of pitch error and rates of roll error. If these pitch and roll errors pass a threshold, we determine that we have a motor failure condition. Then, based on the sign of the rate of pitch error and rate of roll error, we determine which motor has failed. We can determine from this picture how the signs of the errors can help us determine which motor has failed. After comprehensive testing, we found out that our system is pretty accurate with an accuracy of 97.56%. Now, once the filter has identified the failed motor, this filter triggers an emergency control logic. The control system is built as a cascade of controllers. At the top level is a position controller that determines where the drone should go. Normally, it would command roll, pitch, yaw and thrust. In this case, the position controller outputs just two references, one for vertical thrust and one for pitch angle, ignoring yaw. The pitch controller is a custom PID control loop that tilts the drone to desired pitch angle. Meanwhile, a thrust controller, another PID, adjusts the total upwards thrust to control the descent rate. The outputs of these controllers are then passed to a control allocator. This component converts the desired thrust and pitch commands into individual commands for the remaining rotors. Finally, there is a normalizer block because the controller might produce values outside the 0 to 1 range that motor expects. The normalizer scales the outputs appropriately. In practice, we experimentally determine the PWM value needed to hover normally and use that as reference. All commands are normalized around that hover setting. We also impose rate limits so that sudden jumps in throttle are smoothed out. The best part about this implementation was that this entire implementation was done on a firmware level. No other computer, no external computer was required. It was all done on the flight controller itself. For our purpose, we used Pixoc flight controller running a PX4 firmware. As we had seen earlier, the frame of reference which PX4 uses is completely different from our mathematical model. So, after detecting a failure, we rotate the drone's body frame to simplify control. For example, if the front left motor fails, we rotate the coordinate axis by plus 45 degrees. If the front right fails, we rotate it by minus 45 degrees. And similarly for 135 degrees or minus 135 degrees for rear failures. This realigns the two remaining working motors symmetrically around the new horizontal axis. In effect, the damaged quad becomes like a simple two-propeller helicopter tilted at an angle. Mathematically, the drone's attitude and angular rates are multiplied by a 2D rotation matrix plus minus 45 degrees or plus minus 135 degrees depending on which motor died. The custom controllers then operate in this rotated frame. After computing the needed tilt and thrust, the control allocator sends normalized commands to each physical motor. Because only two motors are active, the control allocator ensures that disabled motor's command is 0 and also the motor which failed also is commanded 0 and renormalizes the others. By using the known hover throttle and controller's desired thrust, which we found out using simulations, all motor signals are scaled to normal hover power. Limits are set so that command never exceeds the safe bounds or change too abruptly. This results in a smooth redistribution of thrust to the remaining rotors, compensating for the missing motor in real time. Mathematics behind whatever was discussed in the previous slide. So you can see the different rotation matrices for different rotors failure conditions. Also you can see how we determine what angular velocity should be given to each rotor using the values which we know, and also how we normalize these values based on whatever hover values we have determined experimentally. We saw experimentally that in our SITL we needed an omega value of 0.57 for the drone to just hover, and based on that we have normalized the omega. On the firmware level, we had created many custom messages and commands, also many modules in PX4. So this slide gives an overview of what we created and what each function, messages and files does. What changes we did to the already available models on PX4 for SITL. So normally a drone is preferred to have a 2:1 thrust to weight ratio, but in our case, since after motor failure there are two rotors which are not spinning, we had to artificially reduce the weight of the drone so that the drone could maintain that 2:1 ratio. See some simulation results. First, let's see how our motor failure detection works. So we are doing this simulation on gazebo. We set artificially one of the motors to have a PWM value, maximum PWM value of 0, and this is how our module has detected which motor has failed. Let's see how our landing algorithm works. So we have made a custom command in which if we command any of the rotor to fail, it will fail that rotor and it will detect the failed motor automatically and then land the drone. So we type in that command. So first we take off the drone to required altitude, then be ready with the command to fail the first rotor. We wait for the drone to gain sufficient altitude and then activate the command. It detects which rotor has failed and it's landing. It spins and lands safely. Now let's see how are the results of this test. Our system in simulation. We used a special motor failure induction command to deliberately cut power to one rotor during flight, simulating a sudden failure. The drone sensors and this control software then took over automatically. In the test, after the failure is triggered, the drone enters emergency landing mode. The custom controllers pitch the drone slightly and throttle down to descend gently. We report that the controlled descent takes about 4.6 seconds from the failure point to landing. For context, this is roughly 1.8 times longer than free fall drop from the same height, meaning the drone actually slowed down its fall significantly. The average downfall acceleration during the fall was minus 1.24 meter per second. Here you can see that we trigger, so this is the acceleration versus time graph. In this we trigger our error here, and for a brief moment where our system has not yet detected the motor failure, our drone free falls at 9.8 meters per second. But as soon as our controller kicks in, the acceleration is controlled significantly from 9.8 meters per second to 1.24 meters per second. These metrics show that Quadrotor was indeed breaking its descent under control rather than plummeting. In summary, the simulation demonstrated a stable emergency landing. The drone pitched forward, let itself spin, and touched down safely without ground impact forces. All remaining degrees of freedom, aside from yaw, were managed by PID controllers, validating the concept. It is worthwhile to note that the approach which we have adopted here is pretty scalable. The prototype we used for simulations was a lightweight test drone weighing around 0.7 kg. Since our approach is scalable, we believe the same control logic could handle a full-size 2 kg quadrotor, for example, a heavier delivery drone, as long as the motors have enough thrust margin. In other words, by adjusting thrust set points, the emergency landing controller can produce the extra lift needed for larger vehicle. The PID gains might need tuning, but the architecture itself remains valid for the heavier drone. What's next for this work? Looking ahead, we see possibilities beyond just landing. We have implemented currently a position controller which can help the drone hover. But in the simulation which you saw, we just showed landing. That's because we put a fixed value on the position controller and we asked it to land. But considering our architecture with proper tuning, it could be ensured that our drone not only hovers but also can navigate in space. So even with a motor failure, our drone can go to from point A to point B without any issues. Such capabilities would mean a drone could recover its composure mid-air rather than immediately dropping, a valuable safety feature for autonomous UAVs. In summary, our project developed an innovative emergency landing system for quadrotors with one motor failure. The innovations include a digital filter that quickly identifies which rotor failed with high accuracy, about 97.5%, and novel control strategy that sacrifices your control to save the drone. We model the imbalance caused by the failed motor and use only vertical thrust and pitch to guide the descent. Our system architecture, custom PID loops for pitch and thrust, plus a clever rotation of body frame ensures the remaining two rotors can work together smoothly. Simulation results showed the drone could land safely in about 4.6 seconds instead of crashing, proving the concept. The approach was tested on a small 0.7 kg drone and is designed to scale up to a 2 kg vehicle, with the promise of future upgrades enabling post-failure hover or even a limited flight. Beyond technical details, our project highlights effective teamwork at the InterIIT ideaForge competition. Our team combined control theory, signal processing, and clever programming to tackle a real-world problem. These implications are significant as drones become ubiquitous. Being able to survive motor failures can make UAVs safer for applications like delivery, inspection, and emergency response. Majority of the math for our work was inspired from this paper. Please do consider reading it if you want to learn the modeling of our system. Please do consider subscribing or liking if you like the video. Also, I would like to thank all the team members who have worked tirelessly on this project.